Let's have a look at some of the factors which affect how well enzymes can do their job. Enzymes need the right conditions, such as temperature and pH, for them to work best, and these are called the optimum conditions. First of all, we'll have a look at temperature. Changing the temperature changes the rate of an enzyme's reaction. Like with any reaction, a high temperature will increase the rate at first as there's more kinetic energy, so the enzyme and the substrate will move around a lot faster and have more successful collisions. But if it gets too hot, some of the bonds holding the enzymes will break, and this will then destroy the enzyme's special shape, and so it won't work anymore. This is when we say the enzyme is denatured. We'll come to that a bit later on, looking at what that actually means in terms of the structure of the enzyme. First of all, let's have a look at this example graph. As you can see, it's a graph showing how temperature affects an enzyme's rate of reaction. Down here you can see the temperature is very low and the reaction rate is pretty much at 0. Here the enzyme is inactive. It's not warm enough, and therefore there's not enough kinetic energy for the enzyme to work properly. As the temperature increases, the enzyme's activity also increases and the rate of reaction goes up steadily. You can see, if you look along the x-axis, the enzyme is working at its maximum rate at between 35 and 40 degrees C, approximately 37 degrees. Here is where the enzyme's reaction is at its maximum, and so we'd say it's working at its optimum temperature, and if asked to label, we would label somewhere on the x-axis showing that the enzyme is working at its optimum temperature. As the temperature increases past around 37 to 38 degrees, we can see the rate of the reaction starts to decrease or go down at a steady pace. And by the time the temperature is increased beyond about 40 to 45 degrees and so on, the enzyme no longer will work. This is because the enzyme is now denatured. This means it can no longer do its job properly, and we will have a look at how denaturing affects the structure of the enzyme in a few minutes. The optimum temperature inside the human body for the digestive enzymes to work is usually around 37 degrees. Let's have a little look at the next example. Okay, here we can see what this word denaturing actually means in terms of the structure of the enzyme's protein. So here's a diagram of a normal shaped enzyme, and you can see the active site, which we looked at in the last clip, is completely intact. If the temperature is increased beyond the optimum, so in the previous example that was beyond about 40 degrees, we can see that the enzyme's shape changes. So the structure of the protein, or the amino acids that make up the protein, becomes slightly deformed, and we can see this active site is now looking rather strange. If you think now, if there was a substrate that was trying to attach to this active site, it wouldn't be able to do that because the active site has now changed. So the enzyme would no longer work. If the enzyme would no longer work, this means the reaction could not take place because the substrate or the reactant would not fit to the active site, and therefore we could not get the products. Once an enzyme is denatured, it is irreversible. That means it cannot be changed back to its original normal structure. It is also the same for pH. pH is affects the enzyme's activity. different enzymes will work in different pHs. So again, if an enzyme is placed in the wrong pH, the enzyme will become denatured. This means exactly the same as I've just explained. The active site changes shape, the structure of the protein is incorrect, and therefore the enzyme cannot work properly. So just to recap, enzymes have an optimum pH and an optimum temperature where they work their best. If it gets too high or too low, it will affect the enzyme's activity, and for pH it will affect the bonds that hold the enzyme together, and so the enzyme is no longer working properly. Here's just another image, and we can have a look at a graph here which looks at pH. We can see you've got 3 different examples of enzymes, digestive enzymes. We've got pepsin. If you're given a graph that looks like this, you can see if it was asking you to label the optimum for pepsin, you would be looking at about pH 2 down here. So this is obviously an enzyme that works in an acidic condition. Over here we've got pancreatic amylase, and we can see the optimum is around pH 8. So this is an enzyme that would work in a mild alkali condition. Obviously you can see the enzyme is working at around pH 7 and also around pH 9, but it's at its optimum at pH 8.